Okay, question 16. In this question, use g is 9.8 meters per second squared. So, straight away, that tells us we are dealing with accuracy of two significant figures. The diagram shows a box of mass 8 kilograms being pulled by a string so that the box moves at a constant speed. That's going to be important over a rough horizontal board. The string is at an angle of 40 degrees to the horizontal, and the tension in the string is 50 newtons. So there's our diagram. The coefficient of friction between the box and the board is mu. We want to model the box as a particle and show that mu is equal to 0.83. Okay then, let's put that info on the diagram. So first of all, let's deal with the string. So we know the force, or the tension, is working up and to the right, and has a magnitude of 50 newtons. So I'm just going to write it as 50. Now what we can do is split this into the horizontal and vertical components. So 50 is the magnitude of this vector. So we can work out the vertical component using trigonometry. So we know that sine of 40 would be the opposite divided by 50. So the opposite is 50 sine of 40. Now very similarly, the horizontal component, let's call him F, is going to be 50 cos of 40. Okay, now we know the weight of the box acting downwards is 8. G, the force acting up, is the normal reaction force. Now we know that the box is moving to the right. So the resistant force is going to be mu times the normal reaction force. Now we also know that because the box is travelling at a constant speed, then the acceleration of the box is equal to 0. So that's what we've got up to this point. Okay, so we know that the box is only moving horizontally, so there is no vertical movement. So that means our vertical forces are in equilibrium. So we know then that R add 50 sine of 40 to our two vertical forces, we know that they are equal to our downward force 8g. Therefore, R is 8g minus 50 sine of 40. So now we know what R, our normal reaction force, is. So, what we also know is because there is 0 acceleration, we know that mu R so our resistant force and our driving force of 50 cos of 40, well, we know that they are equal because they are in equilibrium. So we know what R is. So mu times 8g minus 50 sine of 40 is equal to 50 cos of 40. Therefore, mu is 50 cos of 40 over 8 times 9.8, which is g minus 50 sine 40. Now if you put that into your calculator, we do indeed get 0.83226. Cool. 16b. One end of the board is lifted up so that the board is now inclined at an angle of 5 degrees to the horizontal. The box is pulled up the inclined board. The string remains at an angle of 40 degrees to the board. The tension in the string is increased so that the box accelerates up the board at a rate of 3 meters per second squared. Part 1. So there's the diagram. Part 1 wants us to draw a diagram to show the forces acting on the box as it moves. Okay, so that is our inclined board, and let's model our box as a particle. Okay, so let's see. We got string, and that has tension pulling the box up the inclined board. We're going to have the normal reaction force, which is perpendicular to the board. We're going to have friction trying to hold us back. So now that we know what mu is, that's 0.83 times the reaction force, and then we've got weight pulling us downwards. So that is all the forces acting on the box. Okay, then B part 2 wants us to find the tension in the string as the box accelerates up the slope at 3 meters per second squared. 7 marks. Good times. Okay. So, let's go back to this diagram. Now we know tension in the string is working like that. Now if we break that into its component parts, just like we did in part 8, we know the vertical component is T sine 40, or the perpendicular component to the board, I should say, and then we know the horizontal component to the board is T cos of 40. So that's what's going on there. Now we've got weight working straight down. So we know that that is 8g. Now what we can do from this is make ourselves a little right angled triangle. So if we draw a line perpendicular to the board, like that, and then across like that, we've made ourselves this little right angle triangle. Now we know this angle here is also going to be 5 degrees. So the hypotenuse of that right angle triangle is 8g. So the opposite is going to be 8g sine of 5, and the adjacent is going to be 8g cos of 5. Now, we've also got the reaction force working perpendicular to the board, and then we've also got friction. So that we're still going to have the same constant of friction because it's the same surface. So we know this is going to be 0.83 R. So that's how things are looking at the moment. Tasty. Okay, so at this point now then, where we have all of our forces down, we need to consider what is happening perpendicular to the board and what is happening parallel to the board. So if we look at what is happening perpendicular to the board first of all, then again we know that the box is moving along the board. So there is no movement perpendicular to the board. So we know then that the perpendicular forces are in equilibrium. So we know that R add t sine of 40 is equal to 8g cos of 5 so we can get an expression for R. We can get that R is, well, 8g cos of 5 is 78.1. So we got 78.1 minus t sine of 40. So we do now have an expression for R in terms of t. Okay, so now working horizontally to the board, we know that t cos 40 now minus friction, so minus 0.83 R. Now we also have another force trying to push us back, and that is this 8g sine of 5. So minus 8g sine of 5. Now we know that that is equal to mass times acceleration. So we are accelerating up and to the right at 3 meters per second squared. So 8 times 3, 8 was the mass of the box, gives us 24. So what we can say at this point is t cos 40 minus 0.83 R is equal to 24 add 8g sine of 5. So that's nice. Okay, so now, would you believe it, we need to solve these two equations. So, in the second equation, on the right, 24 add 8t sine of 5 is 30.8. Right. Okay. So, we're going to use the first equation to substitute into the second equation. So the second equation becomes t cos of 40 minus 0.83 lots of 78.1 minus t sine 40 is equal to 30.8. Right, expand the brackets. T cos 40 add 0.83 sine of 40 minus 0.83 times 78.1 is equal to 30.8. Now if we add the last bit to both sides, we get t cos 40 add 0.83 t sine 40 is equal to 95.723 on the left. Factorise, so we get t times cos of 40 add 0.83 sine of 40 is equal to 95.723. Divide through by the bracket. T is 95.723 over cos of 40 add 0.83 sine of 40, which two significant figures gives us 74 newtons. Oh, horrible question. I'm going for a lie down.